Here we go. Awesome. Hello, everyone. My name is Kelsey Gilmore-Innis. I'm very pleased to be here in New Zealand talking to you guys about immutable data. Some things do change, like the title of this talk, also my job position. I have been working in Scala for about 3 years now, doing functional programming. I recently took a new position as Director of Technology at Sexual Health Innovations, a tech nonprofit in San Francisco. We're currently building a reporting system for sexual assault on college campuses. You can find out more about it at that website. And it's in Python, so I'm forgetting everything I ever learned here, but I hope to share some of it with you before it all slips away. So that's me. And this is Jenny Holzer. So I know everyone really enjoyed Raquel's talk and all the art, so we're gonna get a little more art, although I will not be making any today. Jenny Holzer is an American conceptual artist who her most famous ongoing project is something called truisms. She does a lot of text-based work. And a truism is a claim that's like so obvious as to barely be worth mentioning. And Jenny Holzer's art takes these truisms and blows them up and puts them in different contexts, t-shirts, projects onto the side of buildings, movie marquees, and in putting them in a different context really sort of deepens their meaning and points out contradictions in them. It's really interesting work. And I think it's really appropriate to the project of sort of immutable data. There's a lot there that is self-evident, but when you dig, there's like a ton of depth there. Shout out to Jen Schiffer and her project VART, or VART, I prefer to call it VART, which is a really awesome series explaining JavaScript and CS concepts through various artists of different time periods. So I was inspired by her in creating this, and hey, you know, at least it's not My Little Pony, so. So let's get started. So what is immutable data? And here we're going to start with the truisms early. Immutable data is data that doesn't change. And that's what mutable means, is changing. So immutable means it's not changing, like inflammable. No. So it's a value that doesn't change after it's initialized. And that's it. No, it wouldn't make a very interesting talk if that was all there is. But I do want to be clear, that's all that there is in this concept. It's very simple, and there's a ton of gems and interesting properties we can derive from that when we start using immutable data in our programs. And it's kind of often described in terms of functional programming, which is like so hot right now. It's in vogue. There's a bunch of reasons why. So you probably have heard it in that context. Certainly when I started doing Scala full-time is when I really began to use immutable data and immutable data structures more often. However, it has like a real use and actual roots in object-oriented programming. It's not a concept that's limited to functional programming. So I'm going to talk about functional programming, but I'm actually going to talk quite a bit about immutable data in the context of object-oriented programming. In fact, I've been a Scala programmer for quite a while, but I originally learned Java, and Java was my first programming language. And my first introduction, is anyone else here a Java person? All right, cool, couple folks. My first introduction to the concept of immutable data was through Josh Bloch's book, Effective Java. Has anyone read that? Yeah, I see some head nods, it's a classic. He has a whole item, it's pretty early on, I think it's like 14, that says favor immutability. And he talks about why, and his recommended implementation for all that Scala likes to toot its own FP horn, immutable data's implementation in Scala is exactly what he says. It's basically you define a variable or a field that has a getter but doesn't have a setter. So you initialize it and you can't set it, you can only get it. He's talking about objects, immutable objects and immutable fields within them, which isn't the only kind of immutability, but that's where I'm going to start, and I'm going to break down why he suggests we favor it, and I'm going to talk about where that came from. So in terms of why, I'm going to tell you one thing I'm not going to talk about. I'm actually not going to talk about thread safety or concurrency. So immutable data is a huge boon to those things. It's much easier to write concurrent parallelized programs when you have immutable data. But that's all people ever talk about when they talk about immutable data. And I think that the benefits, again, it's a truism, it's pretty self-evident, and you can read more about it after my talk. I'm actually going to talk about other benefits that we can get from embracing immutability. That huge benefit is basically, if we break it down even farther, beyond saying immutable data is good for concurrency. What is it actually good for? Well, Basically, the concern with concurrency is that you've got data being modified in unexpected ways by unexpected actors, right? And so the benefit for concurrency is that you can't modify it. We can zoom out a little bit, though. There's different kinds of unexpected actors, and those actors could be a different thread. It could be another core, but it could be another machine, but it also could be other code in your program. It could be other code outside of your program. It could be another programmer. It could be yourself several months into the future. And these are all actors that it's hard to expect and to anticipate all of their actions. And going immutable with our data can actually give us huge benefits in controlling the effects of actions made by those actors. So that's pretty cool. So I'll start with the second benefit that Josh Block mentions after concurrency, which is what he calls failure atomicity. And what he says basically is that because all of the initialization occurs at construction time and it's atomic, it happens once, you know if it's going to fail when you create that object instance. Your success or your failure based on mutability is just resolved once the object is constructed. Again, this is a bit of a truism, but it's really helpful. A lot of the guards that we put in the error checking and the error catching that we build around has to do with unexpected state changes or illegal state changes. So if you can't have a state change, you don't have that class of errors. So that's pretty cool. Another benefit is that you can memoize expensive results. So if you have something that takes a long time to calculate, but once it's done, you can use it again and again. And there's a lot of numeric operations for which that might be true. It also can be true for drawing from a database. And we'll get more into how immutable data interacts with databases later. You can memoize it, you can save it, and you can cache it, and you can access it again and again because you know it's not going to change. And that's really useful. It can be really super useful. Finally, we all want to favor composition over inheritance because inheritance gets really gnarly really fast. And it's simpler to compose immutable objects because, again, when you're talking in terms of maintaining invariance, which is a big part of programming, maybe arguably all you're doing, when you know that the objects you're composing out of, your building blocks aren't going to change, you can say a lot more with a lot more confidence what state your more complex object is in. And it's much easier to maintain those upper level invariants if you know that the building blocks invariants aren't going to change. So having these immutable objects is really useful for favoring composition and for composing complex objects. It basically comes down to simplicity. This concept of invariance only having one set to enforce and knowing they're enforced for all time. And that's the benefit you get from immutable data, from immutable fields and immutable objects. And it does something here, again, completely outside of the functional programming world. It does something that we really trumpet a lot when we're doing object orientation. It meets a goal there, which is hiding the internal representation of an object. One of our big four in OO, of course, is encapsulation. And that's coupling methods to the data that they interact with, right? We want to make sure they're tightly coupled, and we want to hide that internal representation. What's interesting is we often think of that, we tend to blow up data in our head, but every field and variable that we have is data, right? And that state that can change is another form of data. And so actually, it's a form of information hiding if you have a very destructive sense of the word hide, in that if you can't access state and you can't change state, you've effectively coupled that method to that data, which is really useful. We love encapsulation. It's a big deal. It's an important part of doing object orientation well. Does anybody think that's a stretch? I'm kind of stammering, right? It sounds a little bit like a stretch, like I'm trying to pull this over. But ha, it's a trap. Is this a stretch? No, it is not a stretch. And do you know who says it's not a stretch? Alan Kay, who is the father of object-oriented programming. So he wrote a sort of recap of what their goals were and what their thoughts were in designing Smalltalk, which is the big daddy of object orientation and object-oriented programming languages. And in the early history of Smalltalk, he actually literally says this. He says, doing encapsulation right is a commitment not just to abstraction of state, but to eliminate state-oriented metaphors from programming entirely. He talks about the motivations of developing the philosophy of object-oriented programming. And he says, there's the large-scale one, which was finding a better module scheme for these complex systems. But the small-scale one was to find a more flexible version of assignment and then to eliminate it altogether, which is very exciting. I was obviously very excited to find this. He was doing this in the 60s, right? And in the 60s, very early on, he identified mutable state, which is to say any kind of variable or stored information that can be changed, as a danger to clean and simple and maintainable programs. And the way he sort of expresses that is, it's a great read, it's very philosophical, and he talks about how the object, the model that you're making, carries all this significance and intention. And the method suggests its goals. You're giving a lot of meaning when you model an object in object-oriented programming. And he says assignment statements are really low-level goals. They have to do with memory location. They're very low-level. And you'll need more of them to get anything done. And generally, you don't want to mess around with that. And he has this great quote, which I love, which is, when you have a setter on an object, you've turned it back into a data structure. Which I think is very profound. That's a good point, right? And the way that we deal with data structures and the algorithms we use to update them and store them and delete from them are different, and they should be, right? Because it's a more complicated concept. So this doesn't necessarily mean that he believes that everything should be immutable. And the reason why I know this is because when I was digging into this, I found a question on Stack Overflow that someone asked, does Alan Kay mean in the early history of Smalltalk that everything should be immutable? And Alan Kay answered, well, no, I did not, which was very exciting. I love stuff like that. The internet is amazing. But so he points out Smalltalk has setters, right? Like it's not, he didn't literally necessarily mean immutable data. But he said in that Stack Overflow answer, most people who use setters simply use them to simulate direct assignments to interior variables, right? Like we've all written a boilerplate setter before. And this violates the spirit and intent of real object-oriented programming and encapsulation. So if you needed any more justification, you can say Alan Kay says it's cool. So he says, it's not the be-all and end-all of encapsulation, doesn't replace encapsulation, but we really should avoid assignment. Avoid changing a variable after it's been initialized. Favor immutability. So this comes back from the way earliest days of thinking about how we approach programming and paradigms to make programming stronger and better and easier. He doesn't believe that immutability can replace encapsulation entirely. Some people do believe that, though. One of them, a famous one of them, who does believe that immutable data can obviate the need for encapsulation entirely is Rich Hickey, the elaborately coiffed inventor of closure. And there's an interview that he gave where he says, programming through abstractions is excellent, and we emphasize doing that, and you should do that. But look, at some point, someone's going to need to access that data. That's just how it goes. And I think we can all identify with that, right? Where you're trying to program to this pure ideal, but sometimes you just got to get at a field, you just got to get at a variable, you just got to get at a data item. And he says, if you have this notion of private, if you're doing access control in the way that encapsulation does, you're going to need all these notions of privilege and trust, and there's all this complexity, and there's all this rigidity built around it. But if you start with immutable data, there's really little harm you can do by just providing access. And that's the approach Clojure takes. It's immutable by default, which is really interesting. It means that you can throw away a lot of the concepts of privacy and of getters and of elaborate invariant sort of guarantees because you know that it's immutable to start with. Which is really interesting. And so I find that interesting because, Clojure is a functional language and Smalltalk is a very object-oriented language. But both of those guys, who are very smart gentlemen, who we trust for a lot of insight on programming, are kind of pointing out a point here, which is that set, or equals when it means assignment, actually hides a lot. There's a lot going on there that we sort of pretend doesn't happen. And we sort of pretend that, I would argue we pretend that at our peril. So that's sort of an argument for why, even apart from, even in a world where there was no such thing as concurrency, even in a world where you were running things on very large machines, there's a real benefit to the programmer in terms of favoring immutable data. So that's an object-oriented perspective on why you might go immutable with both your objects and your fields. That said, object orientation is important, but I love functional programming. I've done a lot of functional programming in Scala. This has all been from an OO perspective. And talking about encapsulation kind of falls apart when you start talking about functional programming because we separate our functions and our data in the functional world. That's kind of one of the big main brain warping differences between OO and FP. So how does immutable data work in that world? If we know that it gives us this strong encapsulation benefit in the OO world, what do we get when we're doing FP, when we don't quite have that concern about coupling our methods and our data? Quite the opposite. Well, let me introduce you to my favorite image of all time. I put this in every one of my talks. I'm like, there's a GIF version, and when you can get GIF tattoos, I'm like getting it on my face. I love this. It's by Dwayne Nijkamp. It's an illustration of probably how you learned what functions were like in middle school math, right? Where you've got like a box, and you put something in, and you get something out. It has an input, and for the same input, it always gives the same output. And when I say input, it could be a combination of inputs, but as long as the combination is the same, the output's always going to be the same. And one thing you notice about this drawing is that the boxes are opaque. You can't get into the box or get out of the box. And you actually need that. It seems like a detail. It's not just a design detail. It's actually an important point of how functions work. They have to be opaque like that in order to always get the same thing out when you put the same thing in. And the word that we use for this is referential transparency, which I know I just used the word opaque. I'm just trying to keep you on your toes here. But the word that we use for that is referential transparency, and an expression is said to be referentially transparent if it can be replaced with its value without changing the behavior of the program. So in other words, if you have a call to a function, anytime you call that function, you could just replace the value, and the program will run the same. Again, this is almost edging on a truism, but if you stop to think about it, if you're accessing within that function fields that can change, you don't get that guarantee. So you don't have referential transparency. So we need to make sure that we're not accessing things outside of the function's scope that can possibly change. We also call it side effect free sometimes, or pure, which I think is kind of weird. You're mixing up a lot of concepts there, but referential transparency actually is not a math word. It's not a programming word or term. It comes from W.V.O. Quine, who is an analytic philosopher. I was also very excited to learn this because I was a liberal arts person in college, and I had to write this awful term paper on Quine and free will, and I had almost blocked out of my memory, and now I felt yeah, this is useful. It's not. But the term comes from Quine, who is an analytic philosopher, which again should give you a hint that when we talk about immutable data and when we talk about these concepts, we're talking about how you think, not necessarily how you program to a multi-core machine. Not that those are definitely necessarily different, but still. It was borrowed from Quine by Christopher Strachey, who was an early British computer science and a programming language pioneer. And so he stole the term to describe this concept of being able to replace a function's call with its result. And I really liked how he described it. It's very arch and British. He goes, any other features of the sub-expression, such as its internal structure, the number and nature of its components, the order in which they are evaluated, or the color of ink in which they are written, are irrelevant to the value of the main expression. So it's very dry, but it's true, right? The goal here is that you've got smaller sub-programs that are irrelevant to the composition of the main thing, where you can, once you feel good that they're correct, you can just assume they're correct and move on. A word that they use for this in the Haskell community a lot is equational reasoning. Now, you're not doing a proof or math, no matter how much the Haskell guys want to say that they are, but it's a little bit like doing a proof in, say, high school math, where you reason about these little bits, and once you've arrived at a conclusion that you think is true or that holds, a conclusion that you think holds, you can slot that conclusion in to where the greater chunk was and move on, right? And so if you have referential transparency, you can use this equational reasoning to sort of reason out a program in theory on paper even, right? Again, doesn't sound like that big of a deal, but imagine doing that in a program where you're accessing things that are changing all the time. It's very difficult. This sort of substitute equals for equals concept is useful for reasoning and for understanding our programs. It's also, though, really practically useful when you're testing things. When you can decompose your code into small sections that are referentially transparent, you can test those separately and independently, and you get a lot more correctness and confidence in your code. So that's a pretty cool deal. So how do we get that, though? I mean, it's a nice thing to say, right? The color of the ink. But how do we get that in an actual programming environment? Well, in functional programming, we compose functions. We can stick them together to make bigger ones, right? That's sort of how we go. We start from a little and build up. But we need something here that's a little subtle to make this work and to continue to have referential transparency. It's not just that we can't get into the boxes, although that's very important. We also need the things we pass in not to change. Because for it to hold that what you put in the top always gives the same result in the bottom, every circle returns a dodecahedron or whatever, you need that circle to not change. Because if that circle is modified somehow to become a triangle in the middle, it's not going to give a dodecahedron back out. So that's a pretty important, and I found it kind of subtle aspect of referential transparency. You have to have immutable data going in. So this is another sort of argument here for why immutable data can be useful. You can get some of these reasoning properties. And one last word from Strachey before we move on from that is, curiously enough, he says, mathematicians tend to call these things variables, although their most important property is precisely that they do not vary. So that's a nice thing to keep in mind. So I'll try to use values from now on. So functional programming when we're doing functional programming, but also increasingly when we're doing all other kinds of programming, and that's not just object orientation, there's other kinds as well, gotta throw that in there for my prologue friends, is that functions operate on data structures. And that's a really basic functional programming thing. We take functions, we run them over data. And there's more and more computing these days that that's all you do, you're transforming data, right? So in order to get these properties we talked about, we need to have data structures that don't change. And that's where sort of the rubber hits the road when you're talking about immutable data, because I think you can get the concept of oh, you make the val final or whatever, or you don't change the variable. But actually having a whole, potentially very large set data structure of collection of objects and that collection not changing is a little harder to imagine working. Oh no, my computer is gonna go to sleep. Does anyone have a MacBook Pro plug or whatever? One of these? Anyone? Ian, he's on it. Okay, cool. Sorry, I should have had that under control probably. Okay, so data structures that don't change. It doesn't mean that you don't have an append method, right? Because that would be really useless. It would be really hard to program if you could never append to an existing list. What it means is that when you do append, it returns a new data structure. It's not the same data structure. And if you change the original one, the one that you got back when you called append isn't going to change. We call this persistent, and I'm not going to say that word again because I find that very confusing. That's an overloaded word. It doesn't have anything to do with persistent storage. But if you're looking into this later, often the term we call for this is persistent data structure, which means that previous versions are not modified when you add to a new one. The naive way of doing this is just copy on write. So if you're a Java programmer and you've ever worked with strings, you've seen this happen, right? So if you have a string and you concatenate it to another string, it doesn't actually change the original string. You just copy it and you amend it, right? The problem with copy on write is it's really slow, right? Especially if you're dealing with anything big, the minute that you you need to go write something, you've got to copy the whole thing. And in applications where you're writing a lot, you could be in trouble. So that's not really going to work on the kind of scale of data that a lot of us are working with. And that very quickly gets unwieldy. So how do we deal with that? We deal with that by something that we call structural sharing. And what that basically means is if something didn't change, let's not copy it, right? We only need to copy the part that actually is dirty and that changes. And it's a big word and it's a big term and there's lots of theory about it. Thank you, Ian. There's complicated ways of doing it, and I'm gonna get into a very efficient one and show you. But you're familiar with this if you've seen a linked list. So, for example, here with a linked list, if we wanna concatenate two of them together, we don't actually have to, we don't actually change anything. We just add new pointers, and the nodes don't change, right? So if we look here if we want to add x's and y's together, right, and we want to create a new one called z's, what we're just going to do is we're going to copy until we get to y's, and we know y's doesn't change, so we just add a pointer to it. This is simple, right? And this is, if all you're doing is appending, this could potentially be pretty cheap. If you never need to put anything at the end of a list, you're in probably good shape. The problem is if you do ever need to put anything at the end of a list, you could be in trouble. And so, we have this, and we want y's to be 8 plus the old list. But let's say we want to actually change something or append to the end. Here we've got to copy everything until we get to the one we want to change, right? Now, doing that can potentially get really expensive, as I'm sure you're aware, right? It makes sense that that copy itself can be expensive. It also takes up a lot of space. So the trick here that really makes this structural sharing possible at all is some form of garbage collection, is some form of freeing up unused structures. If you're no longer using the old one, we only keep the nodes that are being pointed to. You have to be careful with this. However, you may be overstating in your mind how careful you have to be with this. There's a wide range of approaches to this, but most languages actually can handle it. There's everything from the example, like for example, Haskell's garbage collector is tuned to assume immutability, so it can do much faster things around immutable structures. But even on, say, a JavaScript engine, and I'll talk a little bit about some JavaScript implementations of immutability and cool frameworks that use it. Even on a modern JavaScript engine, you can actually make fairly efficient use of immutable data structures, and you can write to them a lot, so it's kind of surprising. The linked list example is pretty inefficient if you're doing anything but appending, right? But that's not the only kind of immutable data structure we have. With a tree, you get, because of that branching structure, you get a much faster and smaller implementation of structural sharing. So for example, if you want to delete here, you make copies, and you make copies of the node that leads to where you want to insert, for example. But you don't have to make copies of the other one. So you've got kind of half as much work to be done when you're doing a tree. Of course, the degenerate case is that you want to update the thing on the very far left, and then you've got the original linked list thing, and it's a problem. You have to rebalance. That's expensive. Also, you kind of have the problem, not everything is sorted, right? So this doesn't necessarily work for all things. You might need better search performance. It turns out, though, that there's a clever way to deal with that. A tree's not going to work, so we are going to use a tree. The second tree being TRIE, which is short for retrieval, which is just one of the most boggling examples of naming being hard that I've ever run into, or poor naming. It was named by Ed Fredkin, who is a computer scientist and theoretical physicist who's one of the pioneers of the theory that the entire world is a computer, including down to the atomic level. He seems like a fun guy, like at dinner parties, but I can't really endorse his approach to naming things. So I'm gonna say try. I also say GIF, so come at me. I'm gonna say try to distinguish what we're talking about. That said, another word that people use for this a lot is a prefix tree. And this has gotten pretty common, I think, in technical interviews, so you may have encountered it. It avoids collisions that you would have in a hash table by basically breaking up the key. So it's for a hash, it's for a dictionary. But you break up the key and you branch on the individual components of the key. So if you've seen it in a prefix table, you've probably seen it as a way of like looking up alphabetical, or names to phone numbers is another way that people do this, basically. And so like, for example here, if we wanted to get what was stored at the key 10, we would first go down the T branch, and then our next letter is E, so we'd go down the E branch, and then our next letter is N, so we'd go down the N branch. This gives us a big branching factor. It allows us to store a hash in a way, or a dictionary, sorry, in a way that lets us take advantage of structural copying. If you wanted to change what was stored at 10, you would just need to copy the T node, but you could leave the other links, right? So that's kind of cool. And we got this basically by splitting up the key and using that to navigate the tree. So it's useful for a dictionary, but it actually could be useful for an array. If you think of an array as being a dictionary to index to actual value. And so if the keys are integers, that's like a way of handling random index access if you need it in an immutable shared structure. And you can access into an array really quickly that way. So you can store an array that way and still get your guarantees that you have about your arrays that you're familiar with, but you get an immutable array, and you can use structural sharing. How would we break up the key? Because before we broke it up by letters. Well, this is a decimal try as an example. You could break it up based on decimals, right? So in this example, the 364th item, or no, 362nd item is gorilla. So does that make sense for folks? So you would take the index you wanted, and you'd split it up to get each digit, and you'd use that to look up what the item is. This is really pretty efficient, and it's a really shallow tree, right? Because we have 10 separate trees at each one, so the distance you have to traverse is really not very long. It should be fast, except that it involves a lot of integer division and modulos and stuff, right? If I gave you 362 and on a computer you had to break that up into its digits, I mean, it wouldn't take you that long, but in terms of like how fast index accesses, it takes a long time. However, we can be clever, and instead of branching by a factor of 10, we branch by a factor of 32, which does two things. It makes the tree really, really shallow. The max depth is now n log 32, which is effectively constant. If you have less than 1 billion elements in your array, your tree will be at most 6 nodes deep, and you need 35 billion elements to get up to 8 nodes. So this is really, really fast, right? It's basically constant to get to that thing. And then when 32 is not picked by accident, you can use chunks of bits then to represent the array. And you can do all sorts of really clever bit manipulation that I'm not even going to talk about because we like only had 1 cup of tea, right? Including like down all the way to the instruction level in actual implementations of this, with Hamming distance, which is actually a processor instruction on a lot of machines. This is pretty cool. It's really fast, and it's immutable, which is like a thing that you've been told that immutable data structures, access and editing, as well as actually doing this quickly, are not compatible. But here they actually are. And I think that this is really interesting, right? Because yes, there are performance downsides to immutable data. Certainly, copying on write is a very slow way of doing immutable data. If you're doing lots of objects in general, if you're talking about objects, it can be a big downside to using immutable data, although there are also downsides to mutable if you have to use defensive getters and things like that. But it turns out in practice, there are a lot of examples of immutable things that are faster than their mutable components. One example would be Jota time in Java, which is the widely used replacement for the Java time library, and it's much faster, and it's immutably based. And in fact, that tree I just described to you is called a hash array map tree. Try if you're Googling. It's invented by Phil Bagwell, and there's papers about it. And that's the actual implementation of vectors, immutable vectors in Scala, and of closures data structures as well, which are very fast in practice. So there actually is a way to sort of have your cake and eat it too when you're talking about immutable data structures. This is real life. It's things that you use in real life. And so that's a good example of something you may have already used that is immutable and that's gotten all of the benefits of reasoning about immutable structures without sacrificing performance. I want to wind up by telling you a little bit about some other real-life applications that work on a system level. So far we've talked about fields, about individual fields of objects, and we've talked about objects, which in the grand scheme of things are pretty small, low-level components of software. We've talked about data structures, which are higher level and very important to how we program. Let's talk about systems that are based on immutability and ways that we can get these benefits about reasoning, these benefits about encapsulation, and these benefits about safety in a system level or on a software program level. So you've actually already used something that's based on immutable tree structures. If you've used Git. Git's diffs work in this way. Git is append only, in fact, unless you're doing really crazy stuff, but even then, which we all do, I'm sure, if you're on gitshaming.tumblr or whatever. But Git actually is a tree, and Git uses structural sharing to actually represent the current state of your repo. And that's why you can go forward and backwards in Git. So that's another example of how taking this immutability concept and zooming out gives us this concrete benefit, which is that we can go backwards in time, which is very cool. It also can be stored relatively relatively compactly is the grown-up word for that. And this also is sort of explains why Git has its own garbage collector and stuff like that. But yeah, it's basically it's an immutable tree structure. You also have encountered it elsewhere, almost certainly, if you've ever written to a database. So, database, there's some new concepts talking about data and events and reactive and all this stuff, right? But actually, we already store data as append-only events. We happen to just do it on the back end. That's the log when you have a database, when you log each change. And in fact, many, many databases already do this and store this as such when they're replicating. So the replication is, in fact, a stream of events, of change events that operate on the data. And in sum, they create the state of your data. It's append-only on the log. And there are append-only databases now, but this concept is in the back end already. It's already being done for replication in many, many systems. There's there's a movement to sort of treat the log as the base sort of abstraction of data programming in general. There's been posts about it, especially the guys at LinkedIn are doing a ton on this. They have come out recently with SAMSA, which is a stream processing framework. And it took me a while to wrap my head around, what does that mean? That's just like a bunch of words that are really hot right now all in one. I should know about this. But basically what SAMSA does, and it's made to work with Kafka, but in theory it could work with many other databases, it sort of turns your DB inside out, and it operates on that existing log that you're already making for replication. And it handles reads. Basically, each read is just sort of you querying the facts that you know about changes and using them to assemble a state. And it does some caching stuff to build what they call materialized views. I mean, you've used a materialized view, but it's that materialized view is built and can be predefined on your log data. So it actually can be pretty efficient. And the kind of cool thing is that because the log data is, natural is a strange word to use about it, but the log data is standard, right? A lot of times when we do database stuff, you have to sort of plan out what your queries are going to be ahead of time in order to build an efficient data querying structure. And you can, of course, change that, but that takes time and energy as well. The materialized views stuff is much more flexible. And it's a really interesting idea. It's sort of new. It's in its infancy. There's a really good talk about it at Strangeloop about this concept of turning the DB inside out and taking existing log data and finding ways to query that append-only data. This is also the concept behind CQRS, if anyone's done that, this sort of like command query responsibility segregation, which says that you have your write data, you have your read data. The concept there is asking a question should not change the answer, which I also think would be a good title for this talk. But it's a really powerful idea when we apply it to our databases, especially since we have more and more disk space, right? So a lot of the design decisions around databases and around changing data had to do with constraints that we no longer operate under hardware-wise. And there are, in fact, databases that are built explicitly on this concept rather than using an existing log. The main example would be Datomic, which is also part of the Clojure ecosystem. It writes to disk with the same ideas that we have with immutable data structures, right, with that structural sharing. But it writes to disk and then it applies time as a first-class element so that you can do your queries and get the accurate state at the time that you want. There's also a language called Elm. Has anyone heard of Elm? All right, we got one hand, a couple of hands. It's functional reactive programming. The way that Elm works, Elm also, like Datomic, isolates time as sort of this first-class concept. And it uses pure functions to operate on these signals that change over time. And the thing is, I'm saying the word change, right? Like there's no immutability in there. But actually, each of those events is an immutable input to a function. And this is kind of the core idea underlying reactive programming, I think. I don't know what reactive programming is. But from what I can tell, that's the core concept there. And so something that really interesting, like the word reactive, it has change in it. You think it's very changeable. Reactive programming depends very heavily on this concept of being able to operate on immutable data. It just sort of puts on its head what we think of as immutable. And for another vague use of the word React, a completely different React is React from Facebook, which is a JavaScript framework. And React from Facebook operates on the DOM in terms of diffs, sort of like I showed you with Git, right? So the concept being that when changes happen on a web page, they almost always are happening on a tiny fraction of the DOM itself, because especially with single page applications, there's a ton of stuff you can't even see. So React keeps diffs of the DOM, and it's actually really fast to operate on. Ohm is a framework built on top of React, or I don't know, it's related. I'm not sure exactly what the relation would be there, but Ohm is based on React, and Ohm takes those diffs and sticks it into a persistent immutable data structure of the kind that I showed you. And it is blazingly fast because there's so much sharing when you're talking about DOM operations. It is so cool. Like I will be in the bar just like, have you heard about because it's so awesome, and I really encourage you guys to look it up. It's very exciting, and in general, a lot of this stuff is really exciting. I think we're coming to the point where we can. I love that these ideas aren't new. I think that's one thing that's really exciting when you see these guys who are sort of giants on our field that we're building on top of, we're standing on their shoulders, who are being like, oh yeah, we thought of this already. But it's a good reminder that these ideas are solid and they make sense. And now when we're starting to combine them with some of the hardware processing power that we have and some of the more powerful sort of abilities of modern languages, I just think that immutability gives us a lot of really exciting possibilities. So to wind up, I want to put a plug in for a group that I co-founded and moderate, which is called Lambda Ladies, for the women in the room. It's for women who are interested in functional programming. Tell your friends. It's a really cool community, and a lot of these ideas are being, although, as I said, I don't think that they're limited to functional programming. A lot of these ideas are being explored and pushed to their boundaries in functional realms. So if you're at all interested, go to lambdaladies.com, join our group. It's a super fun community. And yeah, does anybody have any questions? No? Okay, well, I will be here and I'll be around, and please feel free to come talk to me about this stuff. I find it very exciting, and I hope that you go home and tell all your friends and fellow programmers to never change anything ever again. Thanks.